Hi, so today I'm going to be talking to you about rangeomorphs. So rangeomorphs are a group of sessile, frondose organisms that dominate the early late Ediacaran deposits around 571 million years ago. And they're characterized by the shared presence of a hierarchical unit of branched architecture termed a rangeomorph unit. And this is present in all known rangeomorphs at different scales. And this simple anatomy has led to a lot of hypotheses being put forward about their origination and diversification, because these represent some of the very first complex macroscopic communities in Earth history. So these hypotheses have centered around an assumed morphogenetic simplicity or a plastic anatomy. So instead of these representing 4 different taxa, they might represent one taxon which responds very differently to different environments. And these hypotheses are based on an assumed homology between entire rangeomorph fronds. So for my PhD, I've been trying to test some of these hypotheses, looking at and of course, almost every aspect of the biology remains contentious. So I've been trying to test these by looking at rangeomorphs from different deposits, different taxa, and different sizes. And so today I'm going to be talking about a few projects I've either led or been involved with during my PhD. So the first is looking at Charnia masoni in collaboration with Dmitriy Grazhdankin in Russia. The second is looking at Hylocolulus fordi, a new rangeomorph from Charnwood Forest, which was led by Charlotte Kenchington. And the third is an undescribed rangeomorph from Newfoundland, which we're calling Eoelanon for the time being. And then I'll talk a bit about what this means about producing a homology scheme and what we can say about where these organisms might sit in the tree of life. So Charnia masoni is quite an iconic rangeomorph. And we have specimens preserved in effectively 3 dimensions from the White Sea of Russia. And this is important because most rangeomorphs are only preserved as external molds, so the information that we're getting is effectively just from the exterior of the organism. And so I CT scanned and have synchrotron scanned these specimens. So if we're looking through the frond, like in YZ, you can see here 2 first order branches are highlighted in yellow and blue, and there's a third. And in rangeomorphs like Avalophractus, we see a central stalk that runs up the middle of the frond, but we don't see that in Charnia. What we see instead is that first order branches emerge directly from a more basal first order branch, and this confers a sympodial central axis on the frond. And it means that first order branches are entirely constructed of second order branches. We can then look at second order branches in more detail. So this is a model of from the synchrotron of 2 second order branches, the branch boundaries. So you can see the blue and the yellow branch are distinct from each other across the known margin. And if we look through, we can't see any evidence for internal anatomy effectively through the entire second order branch, or nothing convincing at least. So we turn back to the external morphology of Charnia. And so Charnia has 4 orders of branching units. And rangeomorphs can display displayed rangeomorph units, typical of taxa like Avalophractus, or undisplayed, undivided rangeomorph units, which is more typical of Charnia. So Charnia had previously only been described as having these undivided rangeomorph units. But we find that Charnia does, in fact, have displayed rangeomorph units, and that these 3rd and 4th, the highest order branches, appear to be swept in one direction in these specimens from the White Sea. And so it seems like these rangeomorph units, because they display this suite of anatomies, they might be rotational variants, and so they're just bound to one margin of a second order branch and are free to move. And this is kind of interesting because if first and second order branches have this tubular anatomy without any evidence for displayed rangeomorph branch architecture, and 3rd and 4th order branches have a different anatomy, so they're the same, then this means that Charnia doesn't fit the current definition of Rangeomorpha, which requires 3 orders of identical branch architecture. So already there might be a greater disparity, morphological disparity in this group than has previously been recognized. So this is Hylocolulus fordi, and Charlotte also made this wonderful model. So it's got this huge holdfast disc, a long stalk, and then a multifoliate crown. And what's really interesting about Hylocolulus is it has this kind of interesting new pattern of growth. So this is typical rangeomorph branching, where you have smaller units sitting on host larger units. But in Hylocolulus and other multifoliate rangeomorphs from Charnwood Forest, so Bradgatia and Primo candelabrum, we see that sometimes larger branches are present where we would expect smaller branches to be. and this is indiscriminate across the whole rangeomorph crown, and it's not present in every specimen we examined. We term this eccentric branching. What we think is going on is that the rangeomorph, the folia are brushing against each other, and this is a form of overcompensatory growth response to neighbour abrasion. And this is common in modular organisms that are alive today. And we use eccentric branching to infer that Hylocolulus, and so perhaps all rangeomorphs were truly modular organisms because the branches display a developmental independence from each other. And this is something that's long been expected but hasn't been previously demonstrated. So this is a specimen of Hylocolulus. So you can see the stalk here, and this is the crown, and this is an outline of what's going on in here. So this branch here is this one here, and this is an eccentric branch. And in this specimen, where we have the crown here again, and this represents this, you can see perhaps more clearly, this is an eccentric branch, this represents this one. And these are present across the folia, as I previously said. So that's quite interesting, I think. And then Eoewenon is, as I said, an undescribed rangeomorph, and where pretty much all known rangeomorphs have a holdfast structure and inferred to have a holdfast structure to bind them to the sediment. We never ever see that with Eoewenon. What we actually see is this filamentous tether, effectively, and these can be quite large, so this represents this one here. And we see it in every specimen that we find, so we have about 20 of these specimens, and they are never associated with a visible holdfast. And so what we think is going on is that we have the frond when it's alive here with like a subsurface runner of some kind. And then we find these specimens, they're all current aligned. So when the frond is felled, it might be that if you have a runner that's just subsurface, it's kind of ejected from the sediment. This might explain why we never see the end of any filament, and we also never see any holdfast. So again, this expands the known morphological disparity of these groups that were historically considered all to be effectively identical. And now we can consider homology across the group. So there have been two previous hypotheses, both put forward by Martin Brazier and Johnny Ancliffe. In 2004, they suggested that an entire Charnia was homologous to one folia on a multifoliate rangeomorph like Hylocolulus. But in 2009, they said that a Charnia was homologous to an entire multifoliate rangeomorph, an entire Hylocolulus. But using the new data that I have gathered, I actually think they were right in 2004. So blue here is homologous characters. So in Charnia, we know that the first order branches emerge sequentially from each other. They're entirely derived or dependent on the more basal branch. So they represent serial homologs of each other. And we have other rangeomorphs where we never see a stalk. It's been assumed to be present, but it might not be, like Bearthucus plumosa or Colmophrons. And so it might be that if these branches represent serial homologs, an entire Charnia is homologous to the frond of a Bearthucus plumosa. But this doesn't work so well when we consider taxa like Avalophractus, which have a central stalk. So because the branches are no longer dependent on each other, it might be that a Charnia is homologous to just one branch of an Avalophractus. And we extend this to look at the benthic reclining forms like Pectinophrons, which is figured here. And then extending it to consider the multifoliate fronds. So where you have multiple folia emerging from the same holdfast, there is again no evidence to suggest that these are completely dependent on each other, and so it may be that Charnia, an entire Charnia frond, is only homologous with one folia of Bradgatia or Hylocolulus. And I think this is kind of interesting when we look at the very oldest rangeomorph deposits, which are less diverse and have been considered to be less disparate as well. So we have fronds like Charnia, and we also have fronds like Trapacia wardi here, which has this clear central stalk. And so between Charnia and Trapacia, there is already a morphological disparity that hasn't really been accounted for, I think, in previous models of the origination of rangeomorphs. So what I hope I've illustrated with these case studies is that there is a greater disparity in rangeomorphs than has previously been considered. But all of this is kind of nice, but to make it work, we need to understand where they sit in the tree. And so there have been two recent attempts to do this. Dicecki et al. Just considered Ediacaran taxa, whereas Hoyle, Cahill, and Hahn considered metazoans and non-metazoans as well. I have done this slightly differently. I've used it in a Bayesian framework, although I've tested it in the parsimony framework as well. And this is what I get. So I get a node with rangeomorphs as STEMU metazoans, which is very well supported. In order to test this further, I created backbone constraint trees and did stepping stone analysis to get the Bayes factors for more derived and indeed less derived placements. And you can see that a stem metazoan placement is supported and decisively supported in many cases. And so it does seem like, given the data, this position is robust in the tree. And this is really interesting, I think, because rangeomorphs display suites of forms of radial symmetry. And we know that early in groups like the Cnidarians, we don't fully understand how the different patterns of symmetry have evolved. If modularity is plesiomorphic to the eumetazoa, we now have evidence of biological modularity in the rangeomorphs as well. So I think this is kind of cool. Thank you for listening.